Hello. In this section we will talk about the hydrostatic pressure distribution in gases. So previously we said that dP over dz equal to minus rho into g, and dP will be equal to minus rho g dz. So we integrate from P1 to P2 and from Z1 to Z2. So if we assume that the fluid is incompressible, that means that the density is constant and it is independent of Z. So we can take out the density out of the integral. So we'll have P2 minus P1 minus rho g into Z2 minus Z1. So mainly this assumption is valid in liquids, where liquids are always can be assumed incompressible. However, in gases the density is not mainly constant, and the density is function of pressure, is directly proportional to pressure, and the pressure varies with the altitude. So we can say that the density is function of the altitude z. So we write dP over dz equal to minus rho g, and we can use the ideal gas law, that says P equal to rho RT, and rho is equal to P over RT. So if we substitute rho into the equation, we will obtain dP over dz is equal to minus P over RT into G. We can rearrange the equation. We write dP over P is equal to minus G over RT into dz. So if we integrate from P1 to P2 and from Z1 to Z2. So now if we assume the temperature is independent of Z, and we can say that this is an isothermal atmosphere. So if isothermal atmosphere condition is assumed, then we can say that the temperature T is independent of Z, and it is equal to T0, which is equal to 15 degrees. So this value is, by international agreement, is equal to 15 degrees Celsius or 288 Kelvin. So we can write ln P2 over P1 is equal to minus G over R T0 into Z2 minus Z1. So exponential to both sides, we will obtain P2 over P1 equal to exponential minus G over R T0 into Z2 minus Z1. Then P2 will be equal to P1 into exponential minus G over R T0 into Z2 minus Z1. So using this equation we can find the pressure in the atmosphere, however using an isothermal atmosphere condition. However, if we say that the temperature is function of the atmosphere, and we can approximate it as T equal to T0 minus Bz, so we can say that the temperature drops nearly linearly with Z, and B is called the lapse rate, and it is equal to 0.0065 degrees Celsius per meter or Kelvin per meter. So for every meter the temperature will drop by an amount equal to 0.0065. So we can substitute the expression of t in the equation. So integral from z1 to z2 of minus g over r into t0 minus bz dz, and here g over r is constant, so we can take out of the integral z1 to z2 dz over t0 minus bz. So if we multiply by minus b, which is the derivative of t0 minus bz, and we divide by minus b, so integral of u prime over u is just ln u. So we will have g over rb, r into b, into ln u, and u is equal to t0 minus bz. So ln t0 minus bz from z1 to z2. So in this case, ln p2 over p1 is equal to g over rb ln t0 minus bz2 over t0 minus bz1. If we say that z1 is equal to 0, that means at sea level we can say that P1 is equal to the atmospheric pressure at sea level. And you can write this equation as ln P2 over P1, and G over RB we can replace it by, so A ln B is just ln B to power A, so we can replace it by ln T0 minus BZ over T0 to power G over RB, and exponential to both sides, we will obtain P2 equal to P1, or the atmospheric pressure, into T0 over T0 is just 1 minus B into Z over T0 to power G over RB. So this equation can be used to find the pressure at a given elevation, taking into account the temperature variation with elevation.